This video is going to look at a couple approximations. So we've been over the binomial series approximation in another video. So I'm going to link to that video, to 7-3. So it was in talking about gravitational potential energy and why we could approximate potential energy as mgh near the Earth's surface. So if you haven't already, please watch that video, the first 12 or 13 minutes of that video, because that's basically what is done here in sections 16.1 and the first half of 16.2, before, and then he just gave another example towards the end of it. So the key takeaway from that is that the binomial series expansion says that 1 plus x to the n is approximately equal to 1 plus n times x plus, and then there's more terms. So if x is small, if x is much, much less than 1, then you can use this, this series expansion. And if n times x is much, much less than 1, you can, you don't really need to keep the rest of these terms. If nx is much, much less than 1, then this is a good approximation to the whole thing, and you can ignore all those other terms. So yeah, the gravitational potential energy near the Earth's surface is a great example of this, and the reason it was originally introduced in that video. So make sure you watch it to talk about the Taylor series and where this formula comes from. The point of this video is going to be to go over some common approximations like this for other common functions, so ones that you'll see over and over in physics. So we'll get to that in a little bit. I want to go over this example. So this is an example where you would use the binomial series expansion. So the probability my car will break down in the next month is 0.5%. What is the probability my car will break down in the next year? So you could probably guess the answer to this, but I want to convince you that you're actually using the binomial series in your head. Okay. So the probability, so we're going to answer this original question right now. And then after we answer this, we're going to look at this example from relativity as well. Okay, so the probability the car breaks down, in a month. Is 1 minus the probability that the car doesn't break down. So the car either breaks down or doesn't break down. So when you add the two probabilities, you get 100%. Car doesn't break down. And notice how this is what we're given in the problem statement. This is 0.5%, but a percent, as expressed as a number, is 0.005. That's a 0.5%. So the probability that the car breaks down in a month is x, where x is a really small number. Okay. So this involves so the probability that the car doesn't break down, or sorry, the probability that the car breaks down in a year. So I don't really care. So the question that's asked, it doesn't matter if it breaks down once, twice, 3 times. We just want to know if it breaks down at least once. So the better way to think about it is it's probably not going to break down to very good accuracy. And it has to not break down 12 times. Okay. So the way to think about this, and the way you thought about it without, so you probably just arrived at an answer pretty quickly, but this is the way that logically you have to think about it. So the probability that it doesn't break down, in 12 months. That means a bunch of things have to happen. It has to not break down in January, it has to not break down in February, it has to not break down in March, etc. And if those are independent events, then you can just multiply those probabilities. So what I'm saying is that it has to not break down 12 times. So it's the probability that it doesn't break down 12 times. And we can read from here, the probability that the car doesn't break down is 1 minus x. If you move this probability over to the other side, move the x over to the other side, this is 1 minus x. So now you can start to see why you might be using the binomial series approximation. So this is approximately 1 minus 12x. So the probability, and we're ignoring terms of order x squared. So the probability that the car doesn't break down is going to be 1 minus 12 times 0.5%. So this is 1 minus 6%, or 94%. That's the probability it doesn't break down. So the probability that it breaks down in a year, breaks down at least once, in a year, is 6%. Okay, so you're actually using the binomial series expansion in your head. You know, if you thought that the answer was obvious from the bat, you were actually doing this procedure. Okay, so before you attack this as being totally useless, you actually use this already. Okay. Now your book gives another example of this, but in relativity. So the total energy, as you'll learn about in relativity. So right now, so in Newtonian physics, we would say the total energy of just a particle by itself is 1/2 mv squared, right? The kinetic energy. Maybe there's potential energy, but that involves interactions with other objects. As you'll see in special relativity, the total energy of just a particle by itself. So Einstein, S-T-E-I-N, that's what this formula is right here. It's mc squared divided by square root of 1 minus, I'll call it beta squared. So beta is the speed of the object divided by the speed of light. Right? Now, normally we're going at speeds much less than the speed of light, and so beta is a really, really small number most of the time for us. So what you're used to is actually this being 1 minus beta squared to the minus 1/2 power. Or, so again, using the binomial series expansion, this is 1 plus 1/2 beta squared, and there's more terms. I'll just put a plus dot dot dot. So this is mc squared plus, and if you plug in back for beta, if you plug in v over c, this term is actually 1/2 mv squared. So what you learn in relativity is that actually, even if something isn't moving, which normally we would say doesn't have any energy associated with it, you know, if it's not interacting with any other object, actually there's a huge amount of energy. That's most of the energy, this mc squared. That's where this formula E equals mc squared comes from. That's the rest mass energy of an object. And then we just say that the rest of it, which is the energy associated with motion, is the kinetic energy. So actually what you've learned before with this 1/2 mv squared, that's going to be modified when you learn about special relativity. So there's actually more terms to it. It's just that the dominant term is 1/2 mv squared. So that's the term that is much, much bigger than all the other terms combined if you're not moving anywhere near the speed of light. Okay, so this comes in handy too, the binomial series expansion. Just to see this correspondence, to see the fact that the two are related, to see why we can get away with using 1/2 mv squared. Okay, because if normally we just track energy differences, we don't normally see this term, assuming we're not building atomic bombs or anything. And all the change in the energy is in this term, because we can't see this term because it's so small. And if we wanted like the correction to it, maybe we wanted to keep just the next most important piece, we could use the binomial series expansion to keep track of the piece that's proportional to v to the fourth. Right? And your book reminds you that, you know, if you don't have to be exact. Like you very rarely get an exact number. Everything we do is approximate. When we were using this was an approximation as well. It's a very good one, if you're not moving close to the speed of light, but it's an approximation. So, you know, I remember starting college and a professor, you know, crossed off 3 and pi, like 3 on the numerator and pi on the denominator, and I freaked out. But really, you know, you have an idea of how accurate you want your answer to be at the beginning of the problem, or how accurate it can be at the beginning of the problem, and you just have to keep that in mind. You know, your answer is not going to be completely exact. Okay, so this is not the last time you're going to see binomial series expansion. So just a couple more examples of that. One of the main takeaways of this video is that I want you to know some binomial, or not just binomial, some Taylor series approximations. There are some that you are going to see over and over again in physics, and you just need to know these basically by heart. So you can derive all of these using the Taylor series expansion method gone over in the other video, the 7-3 video. So I saw how I derived the binomial series expansion there. It has to do with the first couple sections of chapter 16 in Shankar. But it's just Taylor series from like a Calculus 2 class. Okay, these are ones that you need to know. So first of all, you need to know the binomial series expansion. So 1 plus x to the n is about equal to 1 plus nx. And for the most part, you'll just need to know the terms that I'm writing down right now. So rarely will we need this to second order. Occasionally you do, but almost 90% of the time you just need these two terms. Right? Anything for our class, you'll just need those terms. The second one, e to the x. So in all of these, x is some small parameter. Okay, so everything I'm writing down, x is much, much less than 1. So x, you could use it whether it's positive or negative, and it's the absolute value that's much, much less than 1. E to the x, so if you plug in x equals 0, you get 1. So it starts off 1. That's the 0th order term. And if you're just keeping the next term in x, it's x. So sometimes you'll see e to the x replaced with 1 plus x if that exponent is small. And again, that works whether x is small in absolute value and positive or small in absolute value and negative. The third one, which is related to that second one, is log. Now we don't want to do log of x, so we're not going to do this. And the reason for that, if x is small, this approaches negative infinity. Okay, so really we're going to expand this about this point. If x is 0, if you plug in x equals 0 into that function, you get log of 1, which is 0. So actually the first term that matters here is x. And actually you can combine, you might want to try this, you can combine 2 and 3, because these are inverse functions, e to the x and log of x, those are inverses. So like if you do e to the log of 1 plus x, you should reproduce 1 plus x. So you might want to verify you can do that. Well, why don't I do that? So e to the log of 1 plus x. This has to equal, identically, this is equal to 1 plus x. That's not just an approximation, right? So log we can approximate with log of 1 plus x is approximately x. And then e to the x we could approximate as 1 plus x. Okay, so maybe there were potentially more terms here. We know from looking at the left-hand side that actually it's exactly equal to 1 plus x, but we're able to make these replacements, knowing that x is small. Okay, so exponentials and logs. The other thing that will pop up often are sines and cosines. So sine of x, and by the way, x has to be dimensionless. I'm going to scoot this stuff down, actually. So not only is x much, much less than 1, but also x is dimensionless. And x is dimensionless. So what I'm saying here is that you can't take e to the 1 meter. That doesn't mean anything. So that's a sign that you've done something incorrect in setting up your equation. Right? Same thing with log. You can't take log of 1 meter, etc. Sine of 1 meter doesn't make sense. So as you see these in physics, if it's written this way and x has dimensions, then something went wrong. Okay, you can't do 1 plus something with dimensions. Okay, so if the 1 is dimensionless, the x has to be dimensionless. Okay, back to this. Sine of x is about equal to x. And then the next order term here is x cubed. So actually maybe I'll write down the next one. X minus 1 over 3 factorial x cubed. And the reason I write this is that the binomial series, so if sine is odd, then this side has to be odd as well. And so the next term is x cubed. So we hardly ever need this term. We almost always throw it out. But it's nice to know that there's no x squared piece. So in other words, if you keep this just to order x, that's a really, really good approximation, even better than this one, because here there is an x squared piece for the e to the x. Okay. And if we did sine, you'll probably notice that we are going to do the cosine. Cosine of 0 is 1. So the first term there is actually just 1. And then this, like the sine, it alternates in sign. So the first term here is positive, the next one is negative. The next one's positive, the next one's negative, etc. And the same with the sine. Positive, negative, positive, negative. And there are only even powers for the cosine. Okay. So you could probably guess what these next terms are. So actually for sine and cosine, it's easy to remember. You only keep the even powers for cosine, and it's 1 over n factorial x to the n. And the signs alternate. And same with sine. You could probably guess that the next one is plus 1 over 5 factorial x to the 5th. And I guess this one actually, it's not too bad to memorize. This is 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, etc. And they're all positive. So you can actually show if you write out a few terms for sine and then square it, and then write out a few terms for cosine and square it, and you do sine squared plus cosine squared, you'll see all those terms cancel except for a 1. And you know exactly that sine squared plus cosine squared is 1, so that makes sense. They should all cancel out. Okay, so yeah, your book talks about Taylor series of some more popular functions. They talk about the exponential. They don't talk about the log, but that's one that you'll see a lot in physics as well, especially with like physics, like StatMech, thermodynamics, but really more so statistical mechanics in upper division. You'll see the log one a lot. And then trigonometric functions here, and that's it. So rather than go into complex numbers, we'll just call this video right here.